So today let's explore some potentially hazardous electrocution house burners, I mean USB chargers donated by viewers. These claim a fast charging function and they have more USB ports, but the power rating can be fake and they can be even hazardous. They can cause a fire or electrocution because they might come from questionable suppliers. And let's take a look at the marking of this one first. It says 5 volts, 3.1 amps, but shouldn't it be able to supply a higher voltage like 9 or 12 volts for the quick charging? But now let's zoom this because it's absolutely worth it. Cotton, far, tea and door, UEO only. I guess they're trying to say caution for indoor use only, but they managed to spell just one word properly. Nice. Let's try to plug it in, and it seems the previous owner already tried to pry it open, but anyway, let's plug it in, and it seems to have a voltage display. Of course, it seems dim under studio lights. It says 5.2 volts. This is the first USB charger with a built-in voltmeter I see. Let's try to detect a fast charging function now. No PD, no QC2 or 3.0. It seems no protocol capable of more than 5 volts. Let's try to load it using my test load. 1 amp, 1.5, getting close to 2 amps, and it shuts down. It definitely doesn't look like 3.1 amps. Let's keep it running at almost 2 amps for a while. Now it's 1 hour 20 minutes and nothing has exploded. A little bit of thermal imaging here. How am I supposed to open it? Let's also do some thermal imaging of the bare board. And this is the top of the board. Let's use macro lens. And let's get closer. And the secondary electrolytic capacitor is getting baked here at over 80 degrees Celsius. And remember, when it's in the housing, it has to be even hotter than this. And here's the transformer, which is also quite hot, and the other side of the board, where you can see the primary chip quite hot and its snubber network with the diode and a resistor, and on the secondary side, this is probably a synchronous rectifier chip. This is what's baking the secondary capacitor, and the secondary electrolytic capacitor is soldered in the same blob of solder. But now let's explore the board a bit closer. The mains comes in here through this resistor, which might be fusible, but there is absolutely no interference suppression filter. It goes into this bridge rectifier, then into this primary smoothing capacitor, electrolytic 1, and here's the switching chip on the primary side with a snubber network, with a diode, resistor, and this small ceramic capacitor. Here's the primary of the transformer, the auxiliary winding, powering the chip via this diode, some setting resistors here, this interference suppression capacitor between the primary and secondary side, which is safety critical, but it's not a class Y1 safety capacitor, it's just a 1 kilovolt ordinary capacitor, which makes it unsafe. Here's the transformer with some double-sided sticky tape, with this thing never removed. Here's the secondary electrolytic capacitor, a space for diode, but it seems instead of diode there is this probably synchronous rectifier chip. And there is also a 6-pin chip, probably communicating with the devices. It's connected to the data pin pair of this port and this port, and the last port has the data pins just connected one with another and doesn't go into the chip, and the last 2 pins of the chip go to the supply voltage 5 volts and 0 volts. But there is no optocoupler on the board, so there is no way of this chip communicating with this chip. I really don't see how this chip could request more voltage from this chip. I really can't imagine this changing its output voltage. I guess it's 5 volts only. And the small chip is probably just to indicate the current capability, but not to negotiate a different voltage. And there is a resistor powering this display which shows the voltage, and it also could show a current. It has a symbol for amps, but it's weird. The display seems to have 4 pins only, and the entire module is connected just via 2 terminals, so it's probably never measuring the current. And the isolation distance on the board between the primary and secondary side is sort of okay, but the safety is ruined by this non-safety capacitor, and also its pins are nicely bent towards each other to reduce the isolation distance. And of course we have to make an autopsy of the transformer to see the isolation in it, and let's also look at this. Let's desolder it and test it separately. It has a positive and a negative terminal, and this display. I gave it some wires and connected it to my small DIY bench power supply. Let's limit the current to 50 milliamps and turn it up, and it shows 5.2 volts. Basically no matter what I set. Nice. And the red LED is on. It's limiting the current. It seems like this is just LEDs and no active electronics in it. It actually relies on the current limitation of this power supply now. It's basically nothing but bare LEDs hardwired to show 5.2 volts and absolutely no electronics in it. And amazing. It has just 2 pins and it's a fake voltmeter module. It's basically this plastic display mold with 3 digits, and there is nothing behind the first digit. Just some LEDs on this board permanently showing 5.2 volts. Great job, guys. Just several parallel LEDs, or maybe even just one LED, and some segments masked here, and the resistor for the LEDs is actually on the board here. But now of course let's desolder the transformer and see the internals of it. Now the ferrite core opens. Should have an air gap because it's probably a flyback transformer. Some sticky tape and the auxiliary probably. And this is again an absolute disaster. Here is the auxiliary with its pins, and there is a gap in this insulation exposing the secondary, I guess. So it's basically no insulation between the secondary side and the primary side because the auxiliary is on the primary side. Here is a lot of insulation missing, exposing the secondary. Here is the insulation melted. Nice. It's again melted. One more look at this. Here are the ends of the auxiliary. Here are the ends of the secondary. And how this is insulated. Let's remove the auxiliary and explore it further. Here is the insulation which is melted and with gaps, and it's absolutely not made of a thermally resistant material. It's not even easy to remove, it's sort of melted onto the wiring. Here's the secondary, which is made of 2 parallel sections. And here it's next to the primary terminals. You can see the primary pins and the ends of the primary wiring going here, and there is just about nothing between them and the secondary wiring. This is again isolated just by the lacquer on the wire, which was never intended as a safety insulation, and it's just 0.00 something millimeters thick. And if this lacquer fails, you have minus voltage at the output. Removing the secondary, and you can see the ends of the primary with absolutely nothing covering them, and so the secondary was actually pressed onto them here. Nice. And the primary here. Okay, so let's sum it up. The current capability is fake, there is no interference filter, there is a non-safety capacitor between the primary and secondary side, the synchronous rectifier chip is not doing its job of having a significantly lower loss than a diode, and it's baking the hell out of this capacitor. Of course, electrolytic capacitors are very sensitive to heat, so it won't last very long. But most importantly, there are several places in the transformer where the user is isolated from mains just by the lacquer on the wire. Just the standard lacquer, which is not meant for applications where its failure leads to an electric shock. And there is no safety insulated wire with the thick double or triple insulation. And it gets a lot of bonus points for this amazing spelling and even more bonus points for this fake voltage display. So the conclusion is super dodgy. And the next one says QC 3.0 plus PD, quick charger 20 watts, this USB-A port, USB-C port, and it says it can supply 5, 9 or 12 volts. Let's try to see if this one can switch the voltages. No QC 3.0 detected, nice. Trying a different tool, and I still can't request a higher voltage. Now let's test the USB-C port using this soldering iron. It works from 9 volts up, but it doesn't work at 5 volts. Trying if it can request a higher voltage, but it can't. When it says voltage low, it means it's getting only 5 volts. It's trying to request more voltage, but the charger doesn't supply more voltage. Let's try to load it using this at 5 volts, and let's see. 1.8 amps and the charger shuts down. So it's definitely 3 amps and definitely all these other voltages. Let's try to run it near its maximum for a while. After 2 hours it's getting hot but not failing. And now of course the internals. It has the typical smell of electronics getting very hot, and how do I open it? And that's it. It has some similarities with the previous one. We'll do some thermal imaging. Here is the top of the board, and you can see the electrolytic capacitors are not getting baked as much as in the other one. The transformer is bloody hot, especially the windings, and also the board here is bloody hot. So let's see the other side of it. Here's the primary switching chip baking itself at 92 degrees Celsius. And the snubber network also quite hot. And remember, it must be even hotter than this in the box, and also the silicon must be even hotter than the surface of the chip. And here's the synchronous rectification chip. Also almost 90 degrees Celsius. Nice. Of course, if you want to see the markings of the chips. The isolation distance is horrible. They are trying to save it using a slot, and the soldering quality is horrible. For example, this small electrolytic capacitor, well, it's completely loose in the board. And this one as well. It's a disaster. And there's again a non-safety capacitor between the primary and secondary side, and other than this capacitor there is no interference suppression. Just a resistor in series with mains before it goes into the bridge rectifier. And I also don't like how the primary side capacitor and the secondary side capacitor are right next to each other, and so the safety relies on their heat shrinks, which are not meant as a safety critical isolation, I guess. And here's the USB-C port on a separate board. And there's again a small 6-pin communication chip, but again, it can't switch to a higher voltage. It can't communicate with this chip, and there is no optocoupler. And of course the transformer has to come out. Again a flyback transformer with a small air gap in the middle of the core, and the auxiliary. And this transformer seems a bit better so far. The auxiliary keeps some distance from the ends of the secondary here, and no molten insulation. Let's remove it. Here is the insulation under it with no gaps. 2 layers of sticky tape. Here is the secondary, again 2 parallel sections, and here it at least keeps some distance from the ends of the primary. Here the secondary isn't pressed against the ends of the primary like in the other one. Here is the insulation, which doesn't seem to be molten and doesn't seem to have any gaps in it. and 2 layers of insulation and the primary under it. This one is sort of similar to the other one, but at least the windings in the transformer aren't touching. So the conclusion is dodgy. So that's it, and if you like my videos, please consider supporting my channel on Patreon or using the thanks button, because this really helps me a lot. And big thanks to all of you who already support me.